So welcome back. Okay, so where do we stand? Now I'm going to introduce the main tool that is if you want, the core of these lectures, and this is so-called quasi-particle picture. So it's a very simple physical picture that allows you to understand the entanglement dynamics in terms of propagation of free quasi-particles, or at least particles that behave as if they were free. So this idea was introduced in 2005 in a well-known paper by Pasquale Calabrese and John Cardy. So it's JStatMac. Five P0 410. So what is it about? So let's go back to the picture of the spectrum of the many-body Hamiltonian that we use to drive the dynamics. So this is the spectrum. And then we say that basically, so everything happens in a certain microcanonical window, which has the correct value of energy and all the other conserved quantities that the system has. Now let's take our initial state. So the initial state has overlaps with the state of the spectrum, non-zero overlap. Now if the Hamiltonian is integrable, any eigenstate can be thought of as a collection of quasi-particles. So you generate it by filling single particle-like excitations, as you would do in free fermions. So what will happen when the dynamics starts is that these quasi-particles will spread. So we start moving and will propagate through the system. And there is an extensive amount of quasi-particles, a macroscopically large number of quasi-particles, because for a typical quench, you end up in the middle of the spectrum. So it's like you're pumping an extensive amount of energy, okay? And this has to be distributed somehow. Good. So now solving the complicated many-body dynamics is very hard. So we start with a very simplifying assumption. So the simplifying assumption is that we have our state. Our system is, let's say, that is infinite. And let's assume that only pairs of quasi-particles are produced all over the system. So this is a simple assumption. So, okay, now the idea of this quasi-particle picture is that now, so these quasi-particles are mutually entangled with each other, but only the ones that are produced at the same point in space, or at least within, if your initial state is has finite correlation length, at least within the correlation length, okay? So for instance, these two quasi-particles are entangled with each other. They are not entangled with this other pair that is produced far away. Then, okay, let's also assume that these quasi-particles behave as free particles. Okay, so you have this particle here that travels. The trajectories of these two, they cross. Nothing happens. They are somehow, it's like they are not interacting. Good. Now, so basically what will happen here is that the entanglement will be due to the number of entangled quasi-particles that your subsystem of interest shares with the rest. So for instance, let's take, this is our system. Now let's take a subsystem A here, and this is the complement A bar. Now, let's say that there is only one pair of quasi-particles that are produced, for instance here. So, and this is, let's say, the y-axis is time. Now, there is a pair that is produced somewhere here. So there are the two quasi-particles that start moving. So as long as the pair is within one of the two systems, either A or its complement, there is no entanglement between A and the rest, okay? But then you see here there is a certain time t1. So at this time, this quasi-particle, one member of the entangled pair, enters subsystem A. And this starts contributing to the entanglement. Then you see there is also a time t2. So at this time t2, well, in the meanwhile, this is moving along this direction, right? In the time t2, this quasi-particle goes out of A, so it doesn't contribute anymore to the entanglement. Okay, now you see, I mean, this in this very simple picture, if you want to compute the entanglement entropy of a subsystem A at a generic time t, what you have to do is that basically you have to count the number of pairs that are entangled with each other and at that time are shared between your subsystem and the rest. Okay. So you can either do the calculation or you can realize that, yes. Because let's say that all the quasi-particles contribute with the same amount to the entanglement. So the total entanglement is proportional, not the same. Okay, it's not just the number, it's proportional to the number of quasi-particles that are shared. This is. Yeah, it's non-trivial. No, it's non-trivial. So if you want, it's a simple picture that you first use it. Yeah, it gives the correct answer. I mean, it's a simple picture that gives the qualitative feature, and then you can check it in with the free systems. But yeah, there is no. Somehow is what would you like to be true, and then it turns out that it's true. Yeah. Yeah, of course, this we have to assume. I mean, it's the fact that, so there are some ingredients in this picture that you can argue they are true based on intuition. So the Hamiltonian is local, the initial state is local. So basically what it does, it acts locally in space, and then it can only entangle things locally, right? So this is clear. So, and this, yeah. And then you say, okay, my state is homogeneous, so the same thing happens everywhere. Yeah, but there are some other things that is not so clear how to understand intuitively, right? That's a good question. So if you do the other way around, if you start from gapped and you move with the gapless, this is true. You will have sub-bleeding corrections. Actually, there are some intriguing logarithmic corrections that you can get. If you start from a critical state, so I think what will happen is that since, okay, the initial state is critical, then you end up in the middle of the spectrum, so there will be a big correlation length at the beginning, but then the correlation will be destroyed by the evolution, and then I guess it will give just some transient at the beginning. Yeah, but don't take my answer as yeah. Okay. Good. So you can either do the calculation or you can understand things pictorially. So you have again, we have our initial state, and then we want the entanglement at time t. So this is time t. So let's say that we have our subsystem A. I think it's too close, too far. My subsystem A. And then you see that basically the number of quasi-particles that will contribute is proportional, or at least it should be proportional. Okay, so you see that if you create an entangled pair here within this region, one of the member of the pairs will end up within subsystem A, and the other one will be outside, right? So for short time, so basically this is 4t, right? This is so here I'm assuming that velocity is equal to 1, okay? Let's put it here anyway, okay? Absolute value of velocity, even though it's 1. This is at short times. So if you go at long times, so this is so now this is time. Time is large, let's say, and you see that the number of quasi-particles that contribute basically are proportional to this to the area of these two segments here, and this is basically twice the subsystem size. Sorry, 2L. Okay. Now, what does it mean here, short time, long time? You can just draw a better version of these pictures, and you realize that the condition is that so here there are these thetas. So for times, short times, you get this term here. At long times, this theta makes this term vanish, and you get this this behavior here. There is a 2L. Okay. So if we plot this, so if we plot this, we have this behavior. So as I said, for t equal L divided by 2V, so up to this time, you have a linear growth. Then at larger times, so you have just a plateau, and the value is of this sorry, here it looks like it's increasing. So, and the value of this plateau is proportional to L, which is what Draghi was saying this morning, that you basically you get 2 to the L numbers if you want to simulate that wave function. Okay. Good. Yeah. If you put if the subsystem is equal to the system, there are no shared quasi-particles, so you get 0, which is correct. There are other effects that you can check. It works, yeah. I will give you some of these cases. I will show you some cases that allow you to check better this. But before going on, so this is a very simplified picture that was motivated by conformal field theory. So, and where is conformal field theory here is hidden in the fact that, well, not so hidden, is in the fact that all the quasi-particles move with the same speed, with the same velocity, which means that you have a perfectly linear dispersion. So if you have a perfectly linear dispersion, you get this kind of behavior. Well, we would like to go a bit farther to treat realistic, I mean, more macroscopic models. To do that, so, well, we promote this V to a function of a parameter that for now is called lambda. And we also say, okay, the contributions of the quasi-particles to the entanglement, we don't know, but we can parameterize it. We can say that, so each quasi-particle carries a certain amount of entanglement, which here was somehow 1. And this is also a function of lambda. So what is this, this lambda? So this lambda is, you can think of as a label that distinguishes the different quasi-particles. For integrable models, generic ones, this is called rapidity. If you don't have intuition about generic integrable models, you can always think of free fermions. And this is the quasi-momentum. So in general, this V, so for instance, for free fermions, you will have a typical functional form of V. For instance, if you have a tight binding problem on a lattice, this is basically sine. So something like this. Okay. Good. Now, all quasi-particles are independent. So we can repeat this exercise for each type of quasi-particles at fixed lambda. And so what we end up with is basically this. Okay. So this is the formula that you get simply by integrating over the rapidity lambda. So I think one should always stress that this is really non-trivial, okay? This is really non-trivial. So there are several things here that are non-trivial. So you have quasi-particles. You can describe the entanglement entropy, which is a complicated quantity. Think of how you calculate it, right? So you take reduced density matrix, we diagonalize it, it's a mess, right? So still you have a simple picture like that. I think one of the most non-trivial things here is that you can perform an integral over lambda. Okay, it's just integrating by quasi-particles. Okay. Good. So this is the pictorial way of deriving this result. You can also, if you want to be formal, you can also do the calculation, right? So this is A, this is A bar. Then what you have to do is basically this. I think I write it somewhere else. Otherwise I don't see anything. So So this formula is simple, right? So you create a quasi-particle at some point in space X. So you create a pair. Then there is one member of the pair that travels with v of lambda. Then there is another one which travels with v of minus lambda. And then you basically, these two integrals, you count the number of shared quasi-particles. Right? This you can do for as an exercise if you want. So good. So okay. Yeah, I mean, this is so far is phenomenological, right? So, and there are two phenomenological ingredients. So there is this S of lambda and this velocities. So the goal is to show that from microscopic calculations you can derive these two parameters, and then you can check it numerically. Yeah, so it's sorry, an analytic proof is only available for free fermions. Yeah, I will mention the result later. It's volume law, yeah. Yes. It depends. So if you are integrable, it's less than the maximal entropy that you would expect here, but it's still volume law. So the physical intuition is that you have conservation laws, and this somehow, I mean, this you can really see from this picture, right? So you do a quench, then you end up here. So you still have an exponentially large number of states that contribute. Okay. Now, if you're thermal, you only restrict the energy. If you have other conservation laws, you have more parameters to fix. So, and this value would be less than the thermal one. So, at that temperature, of course. Yeah. In MBL, is it volume law? I don't remember. You get log, but it's volume law. Yeah. Yeah. Okay. Yes. So now let me give you some. So this is something that is a bit in the spirit of what Tony was asking. So this derivation, this formula that I gave you is for an infinite system, and you have a finite subsystem. You can also ask what happens if you have a finite system. So now you have your subsystem A, and then you have the total system, let's say with the periodic boundary conditions, and the total, so this is size L, and the total system has size capital L. And then what does it happen? So basically, at long times, you have your subsystem. So the number of quasi-particles that entangle it with the rest is proportional to these two, as I said before. Now, as you increase time, these two segments get farther and farther away from each other. At some point, they hit the boundary. So, I mean, the fact that you have the saturation of entanglement means that you have a continuum supply of quasi-particles that keep entangling. But if your subsystem is, if your system is finite, this at some point will stop. So, in fact, what happens is this. You have the linear growth. Here you have a saturation. Then there is another time. And here there is a time equal L divided by 2V. Okay, so at some point your entanglement entropy will go down to 0. And then it will, so since the system is periodic, the quasi-particles will come back and will entangle again the subsystem with the rest. So, and then this thing will repeat itself forever. So this is an effect that, if you want, allows you to test at a qualitative level that the dynamics of entanglement is due to these entangled pairs. Because if you see this dip, you can argue that it's due to these entangled quasi-particles. Actually, this is really important. So the study of this kind of behaviors, like these dips, like this, so it can be a useful tool to distinguish perhaps integrable versus non-integrable systems. Okay? Yeah. How? This joint subsystem, you can treat them as well. You can guess that the only thing that changes is the kinematic of particles. So in fact, you get similar type of dips also in that situation. There, the quantity, the best quantity to study this phenomena is the mutual information between the two intervals. And typically, what will happen is that, so if you have two intervals, so the mutual information will measure how much. Now, in terms of quasi-particles, how much quasi-particles are shared between this and this. So at short times, the two intervals are far away, so there is 0. Then there are some quasi-particles that arrive and entangle the two, and then they will go out. So and the entanglement will, the mutual information will go down again. So it's something like this. So 0, and then a peak, then a 0. Okay. This is also a similar type of check that things work, and it's also a good quantity to investigate if you want to understand what happens, what is the difference between integrable and non-integrable systems. However, so for non-integrable systems, so we don't have really a perfect understanding, but there are indications that this type of phenomena disappear. I mean, this type of behaviors disappear, and the physical intuition is that. So in integrable models, you have this pair, these quasi-particles, and the quasi-particles preserve their identity during the dynamics, but also the correlation between them remains untouched. When you have a non-integrable system, what happens is that the quasi-particles can decay, or the Hamiltonian can destroy the coherence between them. And you see this is an effect that is purely due to the coherence between the two quasi-particles. And this coherence survives up to very long times because the system is integrable. If you're not integrable, it's not clear. So the most accepted scenario is that this type of behavior disappears. This, and also this kind of behavior disappears. But this is indeed what I was about to say. So there are subtleties. So one subtlety is that what I'm telling you is valid for a perfect CFT model. So basically, all the quasi-particles have the same velocity, which means that let's do this experiment. So I have a subsystem, a portion of a subsystem, and then here I encode some message, okay? So and then quasi-particles spread, but they spread with the same velocity. So if I sit here, in a local region of space, I recover the full information because all the quasi-particles arrive at the same time in CFT. But we don't want to work with CFTs, so we want realistic systems. And there you have a dispersion. Okay, so the quasi-particles have a dispersion. Actually, you can look at this problem of a finite subsystem in a finite box and work out the quasi-particle picture for, also considering the effect of boundaries. And I mean, this is not so trivial, but I give you the result. I mean, it's kinematics, okay? It's not just playing with the quasi-particles. I guess, let's see if I'm able to write this formula. It's huge. And then there's therm plus L over T lambda S of lambda. Okay. Sorry, it's a bit ugly formula. So this is the quasi-particle picture, taking into account these revival effects. Now to have an idea of what happens due to the dispersion. Sorry, here there is this symbol here. That means the integer part of x. So if this is 1.3, this is 1, okay? So you can just play with this formula with Mathematica. So let's say that you take S of lambda flat, okay? All the quasi-particles have some value of entanglement, and then you put V of lambda equal to, let's say, sine of lambda. And then you plot this function, and then you change, you play with the total system size. And then you see what happens. So I can tell you, so this is actually some recent work. Okay. So I can give you just the qualitative result. So what will happen is that this dip will not be perfect, because now you have quasi-particles with traveling with the maximum velocities. They will arrive first, but then at later times there will be the slower ones that will arrive later. So what will happen is that this peak will be like this. Okay, no perfect revival. And moreover, you can, if you take, so if you have CFT, if you change the system size, this dip remain the same. If you have a dispersion, try to take that formula and change, increase L and see what happens. So what will happen is that this dip will decrease, and will decrease in a particular way that you can calculate. So I think the thing that I want to say is that as we mentioned before, so there is a difference between integrable and non-integrable, but even for integrable models, I mean, it's not very easy to really spot this difference, because, for instance, even for integrable models, due to the fact that you have a dispersion, you have this kind of behavior which is somehow similar to what you have in non-integrable. So here the point is that information doesn't get destroyed, the coherence doesn't get destroyed because the system is non-integrable, but just because there is a dispersion, so quasi-particles disperse. Okay. Okay, now I'll give you so let me give the main result actually, so, okay? So let's talk about the quasi-particle picture. For generic interacting integrable models. I give you the main result, and then we'll discuss it a bit. So, the result is the following. So, it's the same formula as before. There is an extra sum, and I will tell you soon what it is. So it's the same formula as before. I forgot this condition. It's the same formula as before, except for this sum. So this sum is due to the fact that if you have, unlike free fermions, if you have a generic interacting integrable model, you have different families of quasi-particles. And at least for all the cases that I know, these correspond to bound states of the most elementary ones. So, okay, take for instance XXZ, a spin chain, you have a vacuum, which is, let's say, the state with all spin down, and then you flip a spin. This is a single particle-like excitation. It's a wave, so it's more complicated than that. Then you can also have the case in which you have two spins that are up, and they somehow want to stay bound together, and they behave as a single object with dispersion and energy and so on, like quasi-particles. And this n is summing over this type of excitations. Now, the number of type of excitation that you have depends on the model. So Lieb-Linear repulsive, you have just one species. Lieb-Linear attractive, you have an infinite number of bound states. XXZ, depending on whether in which region of the phase diagram you can have a finite number of families or an infinite one. Okay. But you see, in this formula, it appears in this sum. So I mean, it's not really a complicated. It doesn't complicate things much. Okay, now what are these two parameters? So I mean, this formula, you can, all these discussions are in this paper. Okay. In fact, so the goal is to determine these two parameters, Vn and Sn. So lambda is the rapidity, as I said before. So n I explained. So Vn is the velocities of the are the velocities, and Sn is the contribution of the quasi-particles to the entanglement. So I mean, they depend on the microscopic details of the model. But still, there is some kind of universality. I mean, these two parameters are universal in the sense that they depend only on thermodynamic information, right? So basically, you can determine them by knowing the GG that describes the steady state at infinite time. So you don't have to care about the full spectrum of the model, but just about the thermodynamic relevant information. Okay, so yes, so before determining these two parameters, I think it's good to have a look at the behavior that we expect from this formula. So if we plot it, okay. So now I'm considering again a finite subsystem in an infinite system. So let us assume that in the model there is a maximum velocity. So if you are on a lattice, there is a Lieb-Robinson bound, so there is no problem. If you consider a one-dimensional field theory, then it's a problem. There is no maximum velocity, but let's consider lattice systems. So this formula predicts that for t less than L divided by 2 Vm, where Vm is the maximum velocity, you have a linear growth as before. And then, unlike this flat behavior that you had in the CFT, now you have a slow increase. And this is again due to the dispersion of the quasi-particles, right? So after all the quasi-particles with the largest velocity contributed, then you still have slow ones that come later and keep entangling the system. And then eventually everything saturates as before. Okay, now, well, a few comments. So first of all, so this, I think now we know, I mean, we argue that there is a linear growth of entanglement, which for the MRG is bad, right? So exponential cost. Also, another important component is that this linear behavior actually is not is generic. So if you take also a non-integrable system, you still have this linear behavior. But there the interpretation is different. So it's not due to the spreading of entangled quasi-particles. Okay. Yeah, actually there is one last thing that I forgot to mention, which is very important. So what is the regime of validity of this formula? So this formula holds, so this is something that every time I submit a paper to some journal, I get this comment from from the referee. So I better be clear now. So this formula holds only for T, L going to infinity, okay? So large times, large blocks, and T by L fixed. So this ratio can be anything, but both T and L have to be large, which means that here there is some subleading correction, for instance, order 1, or something that grows milder with T and L, that we are not capturing. Okay, so this is actually the usual thermodynamic limit, so or hydrodynamic limit. From a technical point of view, for free fermions, this corresponds to the regime in which you apply a saddle point stationary phase approximation. So it comes from there. But it's the regime in which you see thermodynamics, right? Outside of this regime, you have to be more clever to get the result. Okay, so let me see. Yeah, so I think now, so we can, so as I said, as I promised, I keep promising that, so we have to determine these two parameters. And to do that, let us focus first on free systems, okay? So free fermions. Okay, so free fermions. So I have in mind a model that you can diagonalize it exactly because it's free fermions. So if you do that, you end up with the an Hamiltonian which is quadratic. Sum over k, epsilon k, and then p dagger k, bk. Actually, how much time do I have? 10 minutes. Oh. Okay. Yeah, so actually let me give first the answer, and then we'll do the calculation for free fermions to the next lecture, okay? Okay, so we have to determine the velocities of the quasi-particles and their entropy. So the key observation here is that at the very beginning, we assumed that we have our subsystem A, and then there is a local equilibration to a GG. So eventually, so the entire subsystem is described by the GG density matrix. Okay, so you have a GG because we have an integrable model, and so for a GG, so GG is a statistical ensemble with some entropy. So the entropy of the thermodynamic entropy of the GG, and this, as any good entropy, will scale, will be extensive. Okay, will be proportional to the sides of L, and then there will be some prefactor. Okay, now so entropy is extensive. If you consider the subsystem, you will have basically that the entropy will be proportional to the sides of your subsystem, but with the same prefactor, because you say that locally your subsystem is described by GG. So this prefactor. So you know that the quasi-particle picture at infinite time tells you that you relax to a GG. So this means that the entropy that you get from the quasi-particle picture has to be this entropy here of the GG. Okay. And if you remember the formula for the quasi-particle picture, I mean, you have that the final entropy is a sum integral over rapidity of S of lambda. Okay. Okay, you have it's proportional to sides of a subsystem, but then you have this S of lambda. And this S of lambda, I mean, the thermodynamic entropy of the GG is the same expression. And this S of lambda has to be the same. So this is one thing. So the other thing is that, so what are the quasi-particles that entangle the system? So for free fermions, this is actually somehow easy to answer, because so for free fermions, the natural thing to do is to use the group velocities. Sorry, this is K, quasi-momentum. Okay. So the velocities of the quasi-particles for free fermions are completely determined by the dispersion of the model. So you have your free fermion model, you diagonalize it, you have a dispersion, and this is the group velocity of the quasi-particles that you can derive from the dispersion. Okay. This is not the same for interacting integrable models, because there the quasi-particle excitations that you have to use depend on the quench. Okay, depend on the region of the spectrum where you are. Okay, but at least for free fermions now we have so we have the result. So next time we'll work out the details for a quench in free fermions. And then I also, work out in full details a specific quench for the XX chain. Okay. Yeah. So I think for today we can stop here.